Okay, we all ready? We might start up on the second bit. I'll have to clip along a bit because I think this might even be longer than the first bit, which took a bit longer than I thought it would. But the first bit, like last time I gave this, I gave two separate lectures, so I repeated a bit of the first bit, so I'll just whiz through that, entering the modern era. But they're just going through, I'll just go very briefly. The conventional space cell, things were very stable for a long period. Then a breath of fresh air came in the early 1970s. People re-examined the fundamentals of cell design and so on after sticking with a stable design for a decade. Violet cell, all the advantages, all the changes. Black cell. The interesting thing about the black cell is, I regard, is essentially the standard commercial cell is the equivalent of the black cell. It's got all the same design features, the textured surfaces, the back surface field or the dope region near the rear contact to protect the minority carriers from recombining there, and increasingly thin diffusions for the surface diffusion. So the only thing different, well, the main thing different is the way the metal's applied. So for these space cells, the metal were applied by a vacuum type of process. So heat the metal, evaporate it onto the surface of the device. But with a commercial cell, you use this cruder but very effective screen printing approach, where you have a screen with a pattern in it, which are these little holes here, and then you have a metal in a paste form that you then squeeze through where you want it onto the surface. So that screen printing is a cheaper process. And the fact that it's been so effective is one reason why it's inhibited a lot of fancy designs going into production, because it's quite a rugged process that needs quite a rugged cell design to be able to work well with it. So the success of this approach in providing a cheap way of making contact to the cell has sort of led to a situation where it's inhibited evolution in the design of commercial devices until recently. Okay, we've been over that. Okay, so we've already discussed this principle, but I'm going to discuss three principles that are important in solar cell design. This first one I think is known to everyone, but the second two, very few people in the photovoltaic area, even in the theoretical area, I think are familiar with. So this one, the dark light superposition, just you can work out what happens to the device in the dark, work out what happens in one particular situation in the light, and then just superimpose them. So that's the superposition principle. So it applies quite, any decently performing cell, it'll apply quite well to. It's only sort of poorly performing cells that you generally would have problems with it. What we're going to look at now is the effect of having a finite n width to the emitter region of the structure. So cells haven't got infinite dimension, as I've sort of been assuming up till now, but the base can be quite wide, but the emitter generally very thin. So what's the consequences of that? And that was quite an important area, in going from the space cell to the violet and then the black cell. So p-n junction theory, just voltage as a control knob, dialing up in particular the minority carrier concentrations at the edge of the depletion region. So you could calculate a value you wanted here and work out what voltage you need to apply to the junction to get that there, and just sort of set that value to whatever value you want. And then the excess carriers decay back to the equilibrium as you get far enough away from the junction. So we're looking at P-type region, are we? Yeah, I think this has got mangled somehow. No, it is a P-type region, yeah. So we're looking at a P-type region, which is opposite what I should be, but we've got a P-type region, and we imagine that instead of having it go on forever, so we get this sort of exponential decay back to the equilibrium value, we stick a surface at this position here away from the junction region. So there's a couple of situations where you can work out what's going to happen quite easily. If you imagine that this surface has very bad properties, and you can describe the properties by a surface recombination velocity. So the surface recombination velocity just determines the recombination rate at the surface for a given minority carrier concentration. So if you have the surface recombination rate infinite, it means you can't have any excess carriers there, because if you did, you'd have infinite recombination velocities, which is impossible, and so on. So a high surface recombination velocity essentially fixes the minority carrier concentration at this surface here to the same value as in equilibrium. So you can see that does a couple of things, like compared to the case where the emitter went on forever, you know, the most obvious change is you're increasing the slope here. So you increase the slope, and electrons diffuse depending upon this slope. So electrons diffuse in this direction here. If you increase the slope, they're going to diffuse more quickly. So having a high recombination velocity means that you're increasing the electron flow from the junction if you shorten the device by having a finite width of the emitter. If you go the other extreme of having very low surface recombination velocity there, you get the opposite effect. You can maintain very high concentrations at the surface, and you get this type of distribution for the electrons in the p-type region. So you notice that the slope's actually decreased. So you're going to get much lower flows of electrons associated with this type of gradient here. So this is a good situation in that you will have small flows of electrons at this surface, and as opposed to this one where you've got the big flows. So manipulating the surface recombination velocity is important in determining the dark current flows from the junction to the surface. And to get a high voltage output, you want to have low dark current flows. So, so this is a situation that's consistent with getting a high voltage output from the cell. This is going to give you a low voltage. If you pick the surface recombination to have one particular value, this is the diffusivity of electrons. This is the diffusion length. But for one particular value, you get exactly the same that you had before. So this is like a neutral value of the surface recombination velocity. You get no change in the current from the infinite emitter extent. What have we got here? Oh yeah, this is the problem with the conventional space cells. As I mentioned before, you diffuse phosphorus into the surface, and in the conventional cell you diffused it so much of it that you had this region that had phosphorus precipitated out as in as phosphides or something that wrecked the silicon material. So this region here acted essentially as an extended S equals infinity region, as shown here. So that has increased this slope even further, as you can see from this. So that was really bad, not only for the current of the cell, as I mentioned, but also for the voltage of the cell, in that it increases the slopes and hence the currents that flow to the surface region. So this introduces the next principle, dark light reciprocity. So this was first discovered about the 1980s, and still probably not universally known. But if you look at my red book, which was written before this was widely known, you'll find a figure in there. Well, you'll find a problem in there where I analyse a situation that's fairly artificial, but gives a bit of insight into the operating principles of the device. So imagine you've got a PN junction in the dark, except for photogeneration along one plane shown here. So nothing happening in all the device except along this one plane. So just plotting, from this direction, you plot the generation rate, you have the junction there, nothing, 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 then a big spike at that position, and nothing else. So that's a problem that's tackled in the textbook, and it's a fairly simple problem to solve, which is why I introduced it there. But this is the answer that's presented there. Figure 8.3. You get a, if the device is infinitely thick, you get a concentration that decays you get a collection probability that decays exponentially with distance away from the junction, and then on the other side the same type of thing, and unity collection across the junction. So so this is the probability, you know, if you have a plane of generation here, you have this probability of getting collected. If it's close to the junction, you have a higher probability. Right at the junction, it's sort of unity probability of being collected. So that's, you know, so that's quite interesting, but it might look a little bit familiar, that diagram. If you, I think the expressions are actually given in the book as well. So this is the expressions for this decay here. For devices that have finite width. So it's, you know, this is the expression if they're infinite width, but this is the expression if they're finite width. It must be for the case where the surfaces have one of those extreme properties. So this is the, so what we're plotting now is not the carrier concentrations, but the collection probability of carriers as they're generated in different regions of the emitter. So if you have a large surface recombination velocity, you get this expression here. Low values, you get this value. I think these formula are in the book actually. So you know, S equals infinity not only increases the slope of carriers and makes the currents in the device, the dark currents higher, but also it inhibits the collection of photo-generated carriers. So a carrier generator right at the surface has zero chance of getting collected, and then it increases linearly as you get closer and closer to the junction. So those, you know, I think those expressions are worked out in the Red Book, but interestingly, it looks very similar to the distributions for the carriers that I showed just a little while ago, and in fact they're identical. So the, you have this unexpected reciprocal relationship between the performance of the device in collecting photo-generated carriers and the performance of the device in the dark. So two completely unrelated physical situations, but exactly the same mathematics describe the answers that you get. So having a bad emitter not only increases the flow of carriers to the surface by increasing the gradients here, but it also decreases the collection probability of carriers generated from the surface region. But the reciprocal relationship that I want to introduce is that the two are intimately related, so that you can use the same expressions for both of them. I didn't realise that at the time I was writing the book. If I had been a bit more observant, I might have noticed that the expressions were similar or even the same. But it took a little longer for the community as a whole to realise this. And even now, I think a lot of people don't really understand that this relationship exists. But if you want to work out how a solar cell will work collecting photo-generated carriers, you don't have to worry about the light at all. You can just analyse it in the dark, work out how the carriers are distributed through it, and then that'll give your answer for how it'll respond to light. So if you have light that's generated at one plane, this gives the answer. If you have a distribution of light generation like you normally would, you just have to do the integration of the product. So that's an important reciprocal relationship that I think, you know, if you understand that, you'll be ahead of 90% of people in the photovoltaic field. Okay, on to evolution design. We had got to 1974, and that's when our group became involved. So there's a lot of stimulation by this work that had improved the performance. So the question was, you know, how far can you go in improving the cell performance? And the big, you know, the limitations on the current of the cell were pretty well understood. You just need to, you've got so many photons in the sunlight, you just need to collect them all. But what really determines the limit on the voltage output of the cell, that was less well understood. And how do you go about making high voltage devices? So that led to our work here. And our emphasis was on trying to control the recombination properties of this top surface. So I've mentioned S equals naught is good, S equals infinity is bad, S equals naught is the best. So not only in terms of improving the collection of carriers that are generated in the surface region here, but also in reducing gradients and hence dark current flows that limit the voltage output of the device. So this was the first structure that got us a world record efficiency. So we took this idea of improving surface properties to the limit. the oxide of silicon, with the interface between the oxide of silicon and the silicon surface, is the is the secret to the success of silicon in microelectronics. It's got very low defect density and acts as a very ideal sort of interface, low recombination velocity interface. So our idea was just to put that thin layer on top of the surface and then put the metal on top of that. And in that way we could control the recombination of minority carriers, not only in these regions here, but also at the metal contacts. However, there was a limit to how thick you could go with the oxide, because in this region here, the oxide has a low optical index, which is bad for coupling light into the cell structure. Silicon's optical index is very high, about 3.5. Air is 1. So the big contrast between the index of silicon and air, which gives you a high reflection unless you put an anti-reflection coating on. But you need a grading of the index in this direction. So thin oxides were used because light wavelengths are sort of micron or hundreds of nanometers type dimensions. Something that's this thin, only 6 nanometers or 60 angstroms, the light doesn't really see. So you can sneak in a low index layer there and doesn't interfere with the optics. And similarly with the electrons are waves too, but they can tunnel through these very thin oxides. So the oxide doesn't interfere too much with electron propagation if it's very thin, even though it's an insulator. So that design relied on those two properties to reduce the recombination velocity along this interface, and gave it our first world record, which was about 18% efficient by present standards. This structure started to become challenging to make in that we needed different oxide thicknesses in these two regions. So we went for a simpler design, which relied on just one oxide, but small openings in the oxide to make the electrical contact. So the requirements for not interfering with the optics and not interfering with the electron tunneling between the metal and the semiconductor were too contrasting to be able to get the best results with one oxide thickness, and as well as the interfacial passivation properties. So small area contacts was the next design, and just the simplification in the fabrication gave us a big surge forward in performance. So that's one thing we found in our research. Complex structures are also often difficult to make. So the simpler you can keep things, you're likely to get in performance just by perfecting a simpler structure rather than trying to perfect a more complex one. So just going to the small area contacts gave the next big jump. These early devices, these were planar, because to incorporate features like this, we had to use photographic processes, and they're more difficult on the surfaces that include textures. But the next big jump, and quite a significant one because it got us to the first 20% efficient cell in 1985, was to actually incorporate some of these ideas of texturing by using a very refined texturing approach that allowed us to also combine it with photolithographic or the photographic processes that we were dependent on to get very fine geometries elsewhere. So this was what we called a microgrooved structure that gave us the optical benefits of the pyramids I mentioned before, but allowed us to implement the structure with more control than we would have been able to with the pyramids that are presently used. So this is the group that got us to the first 20% efficient cell, and you might recognise some of the faces there, like Stuart Wenham is there somewhere. Chi-Man, who's up the back there, that's him as a young man. These were all my PhD students at the time, so Chi-Man was number 7, I think we figured out. So Andy was number 1 and Stuart was number 2, I think, and then so on and so forth. So we're looking pretty pleased with ourselves, quite justifiably, because 20% efficiency had been regarded as a 4-minute mile of photovoltaics, like something that back in the early 50s when they started analysing these structures, they said, oh, 20% is the best you're ever going to be able to do. All these guys have gone on to do something interesting, and this just shows where they've all turned up, but had a big impact upon the development of the solar industry in one way or another. The next thing I want to talk about a little bit is about light trapping, because we started thinking about that a little bit about this stage. So if you just have a planar cell structure, the light will go through it, and if you had a good reflector on the back, it'll go back through it again and then bounce out. But around this time, people began to get interested in more sophisticated ideas for trying to absorb light in the material, apart from just having a simple reflector at the back. And this guy, Eli Jablonovich, did the first interesting theoretical work in that area, along with Adolf Gerzberger, about the same time. But they showed if you had a configuration like this, instead of just having a planar reflector here, you had a reflector that scattered diffusely, so scattered light in all directions. You could boost the path length in the material. So if you just assumed the light went across once, that's unit 1, but you could increase that unit by 4n² times if you used a diffuse reflector like that. That's really quite an amazing result, because as I mentioned, the index of silicon is 3.5, so 4n² is about 50. So just by a simple approach of having a diffuse reflector on the rear, you could increase the absorption of the wave and make it look as if it was 50 times thicker. So quite a significant change. So a lot of the literature you read, silicon's got a weak absorption coefficient, so never can make an efficient cell and so on. Anyone who says that hasn't understood the theory of that was propagated by Jablonovich back then. This effect sort of completely negates the disadvantage of the weak absorption of silicon by boosting the effective thickness by 50 times. The fundamental reason's really quite simple. You might remember that total internal reflection, if you're coming from a high index to a low, you're beyond a certain critical angle, and the light gets totally internally reflected. So for light closer to normal incidence, you get it bended. You get it bent in the low index material as indicated here, and then once you get to this 90 degree of bending, once you get past that, you get total internal reflection, which is quite an effective reflection strategy. Total internal reflection is essentially 100% reflection of the light at that surface. So if the light comes in this direction, gets sprayed into all directions here, it's only going to be the rays within this narrow cone here that actually can get out the second time. So a small fraction will only have 2 passes if you have a good reflector here, but the rest will be trapped at oblique angles into the material, and they stay there on average 50 times. So that was quite a significant concept. Didn't have to just rely on 2 times multiplying the path length, but you had much bigger values to work with. Patrick Campbell, who's still with the group, and myself extended that formula by pointing out, like the cell doesn't really need to respond to the whole range of incident angles. You often know where the sun is, so that if you restricted the angle of incidence, you could get even much higher. Maybe 1,000 times light trapping if you restricted your angle of incidence by a factor of 20, which is feasible to do if you're tracking the sun. We're also very interested in geometrical light trapping schemes, because these are what you get from texturing silicon. You get regular features rather than these randomizing features here. And because of this factor here, this is what's called an ergodic type of limit. You scatter everything uniformly between all the directions or states that are available. And this is like an engineered scheme where you try and control what's happening. So did these non-organic light trapping schemes have any superior performance to these? And the derivation of this formula here suggested there were situations where you might see it. So Patrick did a lot of interesting work for his PhD on exploring the limits of the non-ergodic or the geometrical light trapping scheme. Eli's quite famous for subsequently to this work inventing photonic crystals that most of you, well, some of you may have heard about. And one day I expect he's going to get a Nobel Prize for that work. But the source of all his thinking about what was happening was this photovoltaic work. So this was one of his colleagues that was working with him at the time. We're talking about densities of states and so on due to the optical parameters of the device structure. So you can see how the thinking was going on within his research team about controlling optical states within the materials involved, and that ultimately led him to the conception of photonic crystals. Okay, evolution of silicon cell design 2. Up till now, the work had concentrated on trying to improve the emitters of the cells in different ways, but there was a jump forward when people started looking at trying to get both the sides of the cell really tweaked in. And Stanford University sort of pioneered this approach because this was the cell structure they were interested in. The light's coming from this direction, so it's really drawn upside down. It's a cell with both the contacts on the rear surface. Unlike the earlier Bell Labs cell that also had both its contacts on the rear surface, the carriers don't go around the edge in this cell structure. They actually have to find their own way across to these contacts. They can't rely on a conductive region to get them over there. They have to just diffuse to these contacts. So it works a little bit differently from the Bell Labs device. But to make this structure work, you have to have really good surface properties, and that got them interested in trying to not only improve the properties of the surface exposed to the light, but also the rear surface. And this shows the world best efficiencies in the laboratory at various points in time. And you might note that since 1983, all of them have been UNSW results, except for one, which was the first successful implementation of this double-sided structure, which produced the first 22% efficient cell in 1990, I think it was. So that's a structure that's quite interesting, and it's actually been commercialised by SunPower. So SunPower make this unique product. This is their product here. So this is the front side of the cell. It's just pitch black. It's got textured surface that those pyramids reduce reflection, and then it's got an anti-reflection coating on the back, on the front as well. So if you do it right, you have this appearance of black velvet from the cell surfaces. And then on the back, there's a lot of action happening. You probably can't really see it here. No, I can't even when I go up, so you've got no chance. But it's actually got very fine lines that run up in this direction to this contact pad, and very fine lines that run up in this other direction to this other contact pad here. So it's, this is its positive contact, and this is its negative contact. So you have the two different polarities of contact that, both of them on the rear. Unlike the normal cell that has contacts on the front, these are very simple to interconnect. You just have to connect this point here over to the corresponding point in the adjacent cell. So it simplifies the interconnection of the cell. So not only do the cells work better, but they're, from an engineering point of view, there's less challenges in integrating them into a module, so the module tends to be more durable as a consequence. There's less stresses and so on upon the wafers in actual field performance. So the modules have been shown to have better durability due to the ease of contacting ease of interconnecting rear contact devices. But we followed suit. We realised we had to do something with the rear of our structures to improve beyond where we got to. So we started working with structures with also attention paid to the rear. So this is a structure that eventually led to 25% efficiency. But what we've done is we've paid attention to the front. This grey region here is silicon oxide. So having the surfaces well passivated, important part of high efficiency cell design. So trying for S equals 0 along all the interfaces. And then on the rear, we also tried for S equals 0 by having oxide along most of the rear, but using these local contact areas to make, to make electrical contact to the P-type region of the device. So this structure has the advantage of being a very good optical reflector. The dielectric layer here improves the metal reflectivity, as well as having good electronic properties due to the small area contacts to the P-type region. Okay, how are we going for time? Oh, well, sort of a little bit left. This is the next principle I wanted to talk about, which is PV LED reciprocity. And I think even fewer people in the photovoltaic industry are probably truly familiar with this, but it's a very interesting principle. Very surprisingly early derivation of the limiting efficiency upon a photovoltaic device was done by Shockley and Queisser. So Shockley's popped up before. He developed the p-n junction theory and won a Nobel Prize for that and other things. And Hans Queisser, who started as a young researcher in his lab. But they found a very fundamental way, which I'm going to talk about, of working out what the limiting efficiency of a photovoltaic device was. This was back in the early 1960s. And that's what it is. It depends only on one thing, the band gap of the semiconductor. So this is the limiting efficiency for any given band gap semiconductor. And these are some of the experimental results for different materials. So they don't all obey the same shape of those curves, but there's none of them that are higher. So the efficiency is sort of, the limit is sort of proven by this graph here. After all these years of development, no one's been able to exceed these limits. So general trend is that you have a optimum efficiency range. In the Shockley-Queisser limit, it's actually a fair range of wavelengths that actually give you close to the limiting efficiency, because these little bumps here represent absorption bands in the spectrum, which give you multiple values for the optimum range. Okay, so the Shockley-Queisser theory was based on a very simple idea. So it was based on the idea you absorb sunlight within the semiconductor material. In actual semiconductor materials, there's a lot of processes that can result in the undoing of that absorption process. So the absorption process creates an electron-hole pair. What you need to stop in a solar cell is that electron-hole pair getting back together. You've got to keep them separated or in their excited state until you can collect them as current out from the cell structure. So in the Shockley-Queisser approach, they said, well, if a solar cell's got to absorb light, you can work out from a basic principle of detailed balance that there must be a certain rate that they optically must recombine at. So photoexcitation process, the reverse process is an electron hole recombine emitting a photon. So the absorption process, the photon comes in, creates electron hole pair. The reverse process is the electron hole pair recombines, emitting a photon. So they said, like in a perfect semiconductor, no matter if it's silicon or gallium arsenide or whatever, the best you can do is have the recombination of electron hole pairs limited by that radiative recombination process, electron hole pair recombining by emitting a photon. So this shows that process. So optical absorption is a reverse process. A photon comes in, excites an electron from the conduction band up to the valence band. This is a reverse process, and they base their arguments on the fact this was the limiting process for no matter how well you prepared your material, you couldn't have the carriers recombining more slowly than determined by this rate. In actuality, there's some other processes that go on in cell materials. So this is an important one for silicon, but rather than emitting a photon when the electron recombines with a hole down here, it can give up this energy by exciting another electron. So you've got to dump this energy that you release if you get an electron dropping across the gap here. Emitting a photon is one way, but an easier way in silicon is to just excite a nearby electron to a higher energy. So that's known as the Auger recombination process. Or what happens in bad material, or even good quality silicon, is this process here, whereas rather than releasing this energy in a single go, you release it in multiple steps. You have defect levels within the band gap that the carriers can drop to, releasing the energy as lattice vibrations. So the electron drops and the whole lattice shakes around it, and you get rid of the energy by giving it to the vibrations of the lattice. So that's the process that occurs in most silicon devices and most solar cells of any material. defect-assisted recombination. So this one you can get rid of in principle, you just got to get rid of the defects. This one's sort of an intrinsic process that not much scope for getting rid of, but there are some. You could redesign the semiconductor material to try and manipulate its the properties of these bands. So something you can do in principle, but not too much. And then this one here is fundamental. If you want to absorb light, you've got to accept that you'll have this inverse process going on at a rate that corresponds in a very clear way to your absorption rate. The higher, more strongly absorbing the material is, the faster this inverse process will be. Okay, so I'll just introduce you to the theory of Shockley and Queisser. So we'll have to digress a little bit into black bodies. So this was very important in the development of, of semiconductor theory, I guess, and quantum physics in general. But black bodies were investigated by Planck around the turn of the century. But what he determined was the equation for the energy distribution versus wavelength of a body that was heated to a high temperature, and a very absorbing body that was heated to a high temperature. A body that was essentially black, absorbed everything that fell onto it. And he came up with this black body radiation law. And not only that, but he had to introduce quantum concepts to be able to explain how he was able to derive that equation. So I think he first guessed at the equation, got that right, and then he investigated what physics were needed to be able to derive that equation theoretically. Came up with quantum effects. So that was the birth of quantum mechanics. So the sun is a black body, or very close to a black body, believe it or not. It never looks too black, but it's a very hot black body. So this is the radiation from the sun outside the Earth's atmosphere. So you have something that very closely approximates the shape of a black body. The radiation coming from the sun actually comes from different depths in the photosphere that are different temperatures. So you sort of get a modulation of this is for a constant temperature for the source of the light, whereas for the sun you have radiation come from different depths that modulates so you don't get the black body spectrum corresponding to a constant temperature, but corresponding to different temperatures at different depths of the photosphere where the light's being generated. But here on Earth you get this space radiation beaten around a lot. So the UV light gets scattered, so the sky is blue. That's the blue light getting scattered around the sky. So, and you also get a lot absorbed by ozone in the upper atmosphere, thank goodness, because these radiations here are quite damaging to life. And then you get water vapor in particular, creating these very strong absorption bands that you can see there, water vapor and CO2. So that you have a pretty messed up spectrum by the time you get to the Earth. But the sun itself, the spectrum is very close to this predicted by Planck. Shockley and Queisser derived the limiting performance from a photovoltaic cell by a very simple argument, simple conceptually at least. But what they said initially was you've got the sunlight coming in, and Albert Einstein was very famous for one of his theoretical insights was that light could be regarded as coming as little particles rather than as waves. So he introduced this idea of the energy of light coming in little packages that are now called photons. So you can regard the light as coming into the cell in little packages, photons. And the balance, there's a balance at the cell. You can't do better than this. If you designed a perfect cell, you'd get a balance between the photons coming in, the photons getting emitted by the cell, and the electrons flowing between the cell terminals. So that's 100% quantum efficiency. Every incoming photon either creates an electron or results in the emission of a photon. So sort of like a photon count balance. So that's been understood for some time. So that's why I said before, easy to figure out the current limit on a cell. You just apply this equation here. So that's one part of the derivation, but not too astounding, that particular concept. But what they did next was really very smart. They imagined, like, if I had a solar cell sitting here on the bench in front of me, one of those very dark solar cells, like the black velvet looking Spectralab cells, and I had it in a box so that it couldn't see any light or anything, how many photons would it be emitting? And say, oh, well, I guess it's probably a black body. It's a very perfect absorber. It's probably better than the sun in that regard. So it'd probably be emitting black body radiation, and you'd be right. So it'd be emitting black body radiation at the room temperature. And then you say, well, oh, that's interesting, but what's the source of that radiation? And you say, oh, well, it's atoms vibrating around, phonons would create some of the low energy light, conversion between phonon energy and light energy. But for energies above the band gap of the material, the most efficient optical processes in the material are the band-to-band absorption processes. So you could argue that for wavelengths above or for energies above the band gap, the source of those photons that get emitted is likely to be band-to-band recombination processes. So the electrons are getting from the valence band up to the conduction band at a certain rate in my solar cell sitting on the desk, and then they're falling back again and emitting the light that then comes out as black body radiation. So this was William Shockley who invented the theory of the p-n junction. So he knew about controlling carrier concentrations by applying a voltage to the cell. He said, well, what happens if I then apply a voltage to the cell? And he said, oh, well, it would exponentially increase the carrier concentrations within the volume of the cell. And if I had good surfaces, S equals 0 everywhere, and long diffusion lengths, the increase would be fairly uniform throughout the cell volume. So what would that do for my radiative recombination processes within the material? So all your carrier concentrations increased exponentially. So, well, it would probably just increase the recombination rate exponentially. And that's basically the Shockley-Queisser theory. You know that the device is emitting black body in thermal equilibrium. You then apply a voltage, and the radiation that it emits is the exponentially enhanced black body radiation. So, Shockley and Queisser derived this expression here, essentially for the power output from a solar cell, an idealized solar cell. So this is the power, the voltage, VQV. Yeah, this is the voltage across the cell, V. This is the photons coming in. So this is the photons coming from the sun. The sun, we saw, or I meant to mention, acted as a black body at about 6,000 Kelvin. So this is the number of photons coming in. We're integrating for energies above the band gap because photons below that energy don't do anything useful in a solar cell. And here we've got the black body radiation at 300 K. So as I said before, if you apply a voltage to the cell, at thermal equilibrium with no voltage across the cell, you'd get this amount of photons emitted by the cell. If you apply a voltage across it, it just gets exponentially enhanced by this factor here. So this is a factor that Shockley was very familiar with from having derived it from for the p-n junction device. So you can specify these functions here. Well, Max Planck did it for us. So you have algebraic expressions for these two quantities here. So this is a calculation that you can do just by knowing Planck's expression for the black body. So eventually this term here will become large enough to balance this one, and that's at your open circuit voltage condition. If the voltage is 0, this term's going to be quite small, and you'll have your current output as just the integral of the black body radiation shown there. The other integration here is just over angles, so that's just from, I probably could have left that out. You probably don't really need that if you define these black body terms in similar quantities. So quite an unusual expression, and really insightful thinking about what was happening in a solar cell. The fact that the power output could be expressed purely by these sort of radiative types of functions. And that's what gives the limit on the performance of the devices. Okay. Just a little bit more detail about that. We showed the black body spectrum for the sun before. That for a device at 300 Kelvin has pretty much the same shape. Well, it does have the same shape. The only thing that changes is the wavelengths where these things like these peaks occur. So, you know, just this scale changes and this one changes quite substantially. The 6,000 Kelvin device has a lot more integrated output than a 300 Kelvin one. But if you look at this wavelength here, the wavelengths corresponding to absorption in silicon are down this end here. So you need a magnifying glass to have a look at this bit here. So that's what I've done there. I've just blown this section up here, and then you stick in silicon's band gap, and this is the amount that appears in that integration that came before. So this is the quantity that's exponentially multiplied as you apply the voltage. So you know, so just using these radiative functions, the only parameter you need to know is the band gap of the material. That'll just change the size of this, as well as the size of the amount of radiation that you collect from the sun. If you look at the actual emission from our devices, which is something we did around the turn of the century, this is what the emission from a silicon device looks like versus wavelength. So you get this peak similar to what we saw in that previous graph, but rather than getting the sharp cutoff shown there, you get this gradual cutoff at the higher wavelengths. So something fairly similar to what Shockley-Queisser theory predicts. I won't bother going into that too much. Yeah, I will. It turns out that this is where this other interesting relationship comes in. You can actually deduce the shape of this by measuring a property of the solar cell that at first sight has nothing to do with it. It turns out that, and this was something that was only discovered 7 years ago, but a very important result which people are starting to exploit in photovoltaics. But this is a paper published there that says that this emission for a general solar cell, this bit here is the Shockley expression. The emission is the black body bit, you know, integrated above the band gap. That's what that term's meant to represent, exponential. But if you multiply that by the EQE of the solar cell, you get the exact shape of this curve. So again, this is a very unusual relationship. You've got one property of a device that at first instance would seem completely unrelated to the other property, but they're very closely linked together. So it's like that reciprocal relationship between current and collection efficiency that was mentioned before. So this is the EQE of one of our silicon cells. It starts to fall to zero near the band gap, and that corresponds to this fall that you see here. This shape here is mirrored in this expression. So this is quite a good way of measuring the near band edge EQE of the device structure, and thinking about advanced cell design concepts. So a fundamental relationship between the, remembering that this term here, this emission term, determines the limiting voltage output of the device. So fundamental relationship between the current collecting ability of the device and its voltage. Okay, well this, we were probably the first to measure the emission of the devices using a CCD camera. These are the guys that did it, Torsten Trupke, who lectures here, and Rob Bardos, who sometimes you see around here. But they took one of our cells, and we said we were interested in measuring the light emission and everything, and they put it under a CCD camera back in 1980 and actually measured its uniformity and so on. And then went on to form a company that does that commercially, because the measurement of that light emission allows you to deduce the EQE and hence the quality of the cell. So this is another one of our PhD students, Linda Kosher, who was around here last year, now working for Trina Solar. But this shows what that instrument does, and there's one in our labs that you may have seen. But BT imaging is the name. That's Bardos and Trubka as the BT. But it's showing on the screen a silicon wafer like Linda's showing in its hand, but it's showing the brightness of the emission. So bright emission means good EQE. So the bright areas here means that part of the cell is working very well. So you see these yellow regions here, the bright regions are where the material quality is best. The blue regions are where the material quality is more ordinary. But by using this technique, it turns out you can work out a lot more about the cell than just the material properties. You can work out things like series resistance and so on. Okay, I'll just finish off very quickly because I've just about run myself out of time. What's happening in the future? So the near future, not the far distant future, a little bit too hard to predict. But as we developed these technologies, we gave them names. So the efficiency that got us above 20% was the PESC, but the next big jump in efficiency that took us past the Stanford result was the PERC. And I just happened to get this magazine recently, the key to higher efficiencies, talking about commercial cells. PERC cells the next big thing. So the whole industry is now trying to follow this sort of trail that we blazed in the 1980s and 1990s in trying to improve the performance of commercial devices. So now that the industry has returned to some profitability, the whole industry is investing in equipment that will allow you to take the efficiency of commercial cells above 20%, and the PERC looks like the most likely structure to do that. But that term and the related ones were terms that were coined in this laboratory. The other thing, so here Stuart Wenham in particular is interested in plating techniques for forming the contacts rather than the screen printing. They overcome some of the limitations of the screen printing approach I mentioned. So we've got laser doped selective emitter processes are one of the technologies that there's a lot of work going on here. And combining front and rear type approaches allows you to implement PERC or even Pearl type structures using that approach. The other cell structure that's quite interesting is the HIT cell. So the HIT bit stands for heterojunction. So you have a silicon wafer that's shown here. It's textured, which complicates the drawing a bit. But instead of forming a junction by diffusion, you actually add a slightly different material, in this case a doped layer of amorphous silicon. So amorphous silicon in the form that's used here has a lot of hydrogen in there, so it really acts like a different material from the crystalline silicon. So by forming these different semiconductor materials, it turns out that you can get very good junction properties. So same type of thing done on the front and the rear. The reason that, so this is an interesting structure in its own right, except that these layers tend to be absorbing and waste some of the photons that come from this direction. So just very recently, in February in fact, Panasonic, who are have been historically the main proponents of this structure, announced a 25.6% efficient device, which is the first one to ever get beyond our 25% efficiency record. But this is what they're doing. They've taken this material off the front where it sort of gammies things up. It's not a really good idea to have this on the front, and they put it on the back. So incorporating the ideas from Stanford about rear contact devices. So they have both the N and P type amorphous silicon on the rear of the structure. So sort of combining two advanced cell technologies into the one. Rear junction idea along with this heterojunction approach using the amorphous silicon. So this is a structure that's recently given very high efficiency and obviously of interest if you're interested in manufacturing high efficiency devices in the future. A lot of other people, I've mentioned the attraction of rear contact devices. This is the emitter wrap-through cell where you put tiny holes in the wafer and bring the doped emitter around to the back of the device and have both contacts on the rear. This might look slightly familiar. It's actually the same structure that was used in the Bell lab cells back in 1954. They had the, you remember, both contacts on the back with a diffuse region wrapped around to the rear. So that's the emitter wrap-through, a lot of interest in that. Or the metal wrap-through. So this one gets rid of metal, all metal from the front. This has the contacts on the back, but some metal on the front to reduce the challenges in doing this with, without metal there. So a more rugged approach to the same idea. Not so near future, I mentioned the theory of black bodies. you can work out that the limiting efficiency on photovoltaic conversion is actually quite high. So it's not the 30% that was calculated by Shockley and Queisser. That just applies for a single junction cell converter. But if you just go back to the basic thermodynamics, entropy and energy fluxes, you can work out for a radiation coming from the whole sky rather than just from the sun's disk, you have about 74% efficiency. And been a lot of ideas suggested, and some of them being worked on here, for getting from the 30% efficiency for a single cell up to 74%, but the best is stacking cells on top of one another as indicated there. So 2 cells you can get up from 30% to over 40, 3 cells to close to 50, 6 cells you get close to 60%, and then a very large number you get close to 70. So not a bad idea. It turns out that silicon's not a bad choice for the bottom cell in such a stack. So the red bars here just show, similar limiting efficiencies as I showed in the previous graph. The green shows the limiting efficiencies if you constrain yourself to silicon as a bottom cell. So very good to, very close to ideal. So this is what I think the ultimate silicon cell might look like. You have a silicon cell and you stick a thin cell of different material on top of it to try and implement, or 1 or 2, try and implement this type of structure without departing too strongly from the basic cell design. So that brings me to the end of the talk, just making sure. So I'm sorry for running so far over time, but thanks very much for your attention. If anyone wants to ask me a question, maybe if you stay back, and I'll pleased to answer them. Thank you.